We have seen that the concept of isolation and object-based isolation can be really convenient in expressing concurrent algorithms, but there's an open question as to how to implement them efficiently. Well, it turns out that there's a related concept called atomic variables, and what they do is they capture a special case, a very restricted case of object-based isolation, but one that's implemented really efficiently in hardware. So let's take an example to illustrate this point. Suppose we have an array of work items, x0, say n work items, and these work items are being accessed by multiple threads, T0, T1 to T sub k minus 1. And what these threads are going to do is try to pick up work from this array of work items and do them. So each of them may have a loop that looks something like this, do, and there's a global shared variable called current, which keeps track of the currently available work item. So they will read current, increment it, and we can assume that current was initially 0, and make sure that the value that they read is within range. So if j greater than equal to n, you just break out of the loop, and otherwise you process the item x sub j, and this can keep on going until it breaks from the loop. So we can have a do while true. So this makes sense with one thread that repeatedly goes through the array. If you have multiple threads, T0, T1 doing this code, we've already identified the issues that could occur. There could be data races in these accesses to the shared variable current, and the way to fix it is with isolated, and by now you know that you could even use object-based isolated. So if current were an integer object, you could make this isolated on current. And the advantage of using isolated over here is the threads will only execute this little logic in trying to figure out the index j in mutual exclusion, and the actual processing of the work items can go on in parallel. And when they're done processing one work item, they can go back to get the next item. This is very flexible. If it takes different variable amount of times to process different items, this can be very dynamic and adaptive. Now, it turns out that this pattern of reading an integer value, incrementing it, and returning it is a very common pattern. And there is a standard class available in Java and many other programming environments called atomic integers. And so what we could do is we could make current an atomic integer. And if current was declared to be an atomic integer, instead of us writing the low-level code to do the addition, we would call something like current dot get and add, and you provide an increment value. In this case, it's just 1. So this call to this atomic integer current, this method get and add, is performed in mutual exclusion with exactly the semantics of object-based isolation. What that means is multiple calls to the same atomic integer will be conducted in mutual exclusion, but calls to different atomic integers can go on in parallel. Atomic variables can be used for other cases as well. So for example, we have atomic references. And a common pattern over there is the compare and set pattern, where compare and set you have an expected value and a new value. And the logic of what's done inside in compare and set is, again, it's isolated with this object, but it checks if the value of this is match is expected, then it sets this dot val to the new value. It also returns true in that case. Else it'll return false. So this whole computation of the if then else is done in isolated, but there's special hardware in modern processors that can implement this pattern very efficiently, just as there's special hardware that can implement get and add efficiently. So what we see is that while you can logically think of your concurrent algorithm in object-based isolated terms, it helps a great deal if you can somehow restrict your isolated sections to match a pattern of an existing atomic variable. And if you can match the pattern for an atomic integer, such as get and add, or match the pattern for an atomic reference, such as a compare and set, your code will execute much more efficiently. It's really important to know about atomic variables and use them when you can, but keep in mind that they enjoy the same kind of high-level semantics that we've learned, which is definitely a step above the lower-level approach of using locks to manage this coordination.